analysis skeleton. We will be talking about the basics, what happens in the finite element analysis. So let's talk about the engineering problems and solution methods. So in engineering problem solution, there are to solve any engineering problems, we have three methods. That is, one is the analytical method, second is the numerical method, third one is the experimental method. So we will just talk about what each one of what each one of them are. So in analytical method, it is basically a method which can give us 100% accuracy to the results using the classical equations. Whatever equations is mentioned for that kind of element or that kind of physics, that equations are used and to solve the problem. It is a closed form of solution and it is only applicable for simple problems like cantilever or simple beam kind of structures. But when we have a more complex problems, we use numerical method. Generally, these are used for more complex structure, as I told, for physical problems. It is basically a mathematical expression of physical body. The results must be validated through experimental or analytical method in the end, because this is an approximation method anyway, and there are different types of methods in numerical. Those are FEM, FVM, FDM, and BEM. We will see about this later. And the third kind of method is experimental method. These methods actually gives actual measurements, but they are time consuming and very expensive setups. For example, the car crash test, as you know, it is very expensive. It is only possible if the physical prototype is available, and then the final results are accumulated from the testing the prototype for multiple times. For example, if you want the results of the deformation of the car, so multiple times the car prototypes must be tested. It makes the process lengthier and costlier. So for example, these kind of methods need sensors, strain gauges, accelerators, etc. So next one is the numerical method. So we are talking about the numerical method. So what does the numerical method means, and what types of numerical methods are there, and what is the role in the product life cycle? So in numerical methods there are basically four types. First one is the finite element method, second boundary element method, third one is the finite volume method, fourth one is the finite difference method. So FEM is basically mostly used method for solving the large physical problems. It is basically an approximation of the solution of the partial differential equations. The applications are basically linear, nonlinear, buckling, thermodynamics, and fatigue analysis. And in BEM, boundary element method, it is basically efficient method to solve acoustics and the NVH, noise, vibration, hardness problems. Just like FEM, it requires nodes and elements, but it only considers those nodes and elements which are outer boundary of the domain. So if the problem is of a volume, then the outer surface is considered, and if the problem is of a surface, then the outer perimeter, the lines are considered. In finite volume method, this method represents and evaluates the partial differential equation as an algebraic equation method. It's used for CFD packages. And the fourth one is FDM. It does the same thing. It converts the partial differential equation to algebraic equation using the Taylor series. But the difference is that during the conversion process, it neglects the high order terms, and it is basically used in combination with the boundary element method and finite volume method to solve thermal and CFD coupled problems. Basically, in particular problems like cantilever beam, the problem can be solved by all these methods, but the difference is in the accuracy and the programming easiness and the solution time of each method. So for in this case in FEM, so it's quite efficient for actually extracting the stress and strain from the any given model. But when it comes to the BEM, boundary element method, it only considers the elements in the outer region, so the inner details of the stress and strain may be poor. It only considers the outer, so that's why it is only applicable. It's only best to solve with the acoustics and NVH problems. When we go to the finite volume method and FTM, it basically used for the CFD packages, and it is really good for solving stress and strain problems, but particularly for the CFD, and it's quite natural. It has some limitations with the complex geometry and the multiple material and different element methods. And second one is the product life cycle. So in product life cycle, it basically comes in this area. So what happens is that first we have a product specification, then it goes to the conceptual design, and then it goes to the ergonomics and aesthetics, design and shape, and then it goes to the standard kind of design model. After that, the prototype is developed, and then it goes to testing, and then simulation is conducted for the stress and strain, and then design for it goes to the manufacturing part, then assembly, then drafting. Okay, but the thing is that this two part of the product life cycles are basically very expensive and costly. So these steps are basically skipped. So what happens is that we directly create a design, and then we use the simulation to find the failure of the product. And if there is some problem, then we have to again go to the this part and repair the design and validate the model, and then it goes to the manufacturing process. So that means after detailed design, the process is directly goes to the simulation part, and if there is an error found, then again the detailed design is corrected. The prototype development and testing steps are skipped because of high cost and time consumption. So next one is the discretization of the problem part. So in this thing, there are different subdivisions. First one is what is the role of FEM with respect to the discretization. Second is the discretization of the problem. Third one is the degree of freedoms. Then the interpolation. Then the element types and accuracy. So in FEM is basically a numerical method, which is also an approximation method. In this method, the actual problem is represented as a mathematical model. In FEM, a continuous body means the mass is distributed uniformly, and it is assumed that the density is also uniformly spread out and doesn't have any discontinuities. Okay, that kind of body is called continuous body, and which has a infinite number of particles, so there are infinite degrees of freedom. This method basically divides the continuous body into finite number of elements, thus restricting with the finite number of degree of freedom with the help of discretization, which is also called as meshing. Okay, so this is basically the abbreviation. So finite element method. Finite means it reduces the degree of freedom. Elements means the calculation is basically done on those of the nodes of these elements. So that means we are reducing the calculation efforts by specifying the number of elements, and there are basically other methods to solve this engineering problem using the elements. So next one is the discretization of the problem. So discretization basically means is dividing the continuous system into finite number of elements and degrees of freedom. Thus, modeling a body is basically dividing it into an equal system of finite element interconnected at finite number of points, which are also called nodes. Okay, as you can see here, it is connected at only finite at these points, not here in between. And what are degrees of freedom? Degrees of freedom is basically the minimum number of parameters that are required to describe the position of any given entity in the space. For example, this is the point in the 2D space, so only we need two parameters. And if it is a line, to describe this one point, we need three parameters, that is xy and the rotation angle. And if it is in 3D space, we need basically three parameters to describe a point. Okay, so that means in 3D space, to describe this line, that means there are two nodes, that means we need 6 degrees of freedom to describe the line in 3D space. And what do you mean by interpolation? Why do we need interpolation? So basically, if there are a number of nodes in a continuous body, which is basically infinite, so then we will get infinite degrees of freedom for the body. So therefore, the total number of equations will be infinite. Okay, the system of equations will be infinite. Therefore, the body is divided into a number of elements, which is also called mesh, and the FEM calculations are done on those nodes of the elements. And then these results are interpolated for the entire domain. So basically, if we take an example of this quad 4 element shown below, the FEM finds the results of the calculation of those nodes. But if you want to calculate the results at unknown point inside the domain here, then we need to interpolate the results. So if we have the results for the 4 points, we use these linear equations as given here, and we interpolate it. And if we want to find deformation here xy, we will just put the xy value here and we can find the deformation at any given point inside the domain. Okay, next one is the element. So what kind of element types are there? So there are 1D element, 2D element, 3D element, and other mass kind of elements. So for example, what is the shape for 1D element? It is just a line. For 2D, it's a quad element, tri element, an R tri element, etc. And for 3D, there are tetra, penta, hexa, pyramid, and there are also other shell kind of elements in 3D. Okay, so what kind of element types we use? Rod, bar, beam, pipes, etc. And for the 2D, it's like thin shell, plate, membrane, plane stress, plane strain. And for 3D, it's basically solid. So practical uses, we use this 1D element for long shafts, beam, pin joints. And for 2D elements, we use practically for sheet. sheet metal parts, plastic components, etc. For 3D elements, we use it in any solid models, for example, transient casing, engine blocks, crankshaft, etc. And there are other elements also like mass element, point element, which are used for advanced cases. So for each software has different names for 2D, 3D elements. So for like in ANSYS, we have plane 42, plane 182, so these kind of elements for ANSYS. And this is basically a combination of all the three, four elements, right? This is basically, you can see it's a solid model, 3D element. This is a shell, this is a plate, 2D. Basically a shell, 2D element is used here, and this is just a shaft, a rod kind of beam or bar kind of element is used, basically a 1D element. And these are basically advanced kind of a rigid element or mass element. So basically it depends upon the type of analysis, geometry, size and shape, and the project time. So kind of what kind of analysis do you want? Does it is a static or dynamic or linear or non-linear, like for metals or plastic materials? So it depends on kind of material you're going to use. For certain kind of materials, you need some kind of elements. For some other, it is some kind of elements. And geometry size and shape. If it's very thin kind of material, then we can basically use the shell. And if it's a very solid kind of model, we will use other kind of 3D metal, 3D materials. And if you're just analyzing the cross section, then definitely we'll use only 2D elements. So it depends upon the geometry size and shape. And next one is the project time. If it is a heavy project or it is a big model, then definitely we need to use a simpler elements which can produce results easily, fastly. So for that, it depends upon the project time also. Okay. So next one is the meshing accuracy. It is nothing but the closeness of the results with compared to the numerical, with compared to the analytical method. So if you have an analytical result, and how close is this method with respect to the our simulation, that's numerical method. So what it means that this accuracy basically essentially depends upon the meshing methodology and what kind of elements you're using. So generally what it means is that if you use more number of elements, then that elements will represent the shape of the model more accurately. That means if it represents the shape accurately, then the results of the calculation will be also more accurate, but it also demands more solution time. So as you can see here in the picture, in this fillet or chamfer kind of thing, if you use 2 elements, 3 elements and 16 elements, you can see these 16 elements basically represents the shape more accurately. So more, if it represents shape more accurately, it also needs more time to calculate, because this number of elements will have that many type kind of that many times of nodes, that many times of system of equations. So it needs more time. So we can also basically see the convergence from these are the number of lines or number of elements, and this is the answer. So as you can see, if the number of elements are increasing, the closeness of the answer is also getting closer to the analytical. Means also the answer is basically 100% accurate when we go to the more number of elements. Okay, but in general practice in engineering, moderate number of elements are considered such that it requires only less solution time and the accuracy is more than 90%. So this moderate level is only required. But what is this moderate level? We will see in the future videos. So next one is the FEA process flow. So in this we will see what is FEA stiffness matrix, how does it how it is formulated, what is direct method, and we will see some example of it, and then the process. What is the basic process? Okay. So in FEA process, we first calculate the stiffness. So the equation for a linear static analysis is basically Hooke's law. F is equal to Kd, F is the force applied, K is the stiffness of the material, and D is the displacement. So usually the force applied is known, is basically the input. Displacement or deformation are basically unknown and we need to find it. And stiffness is basically the material property of the material. We use this to calculate the displacement. So what happens is that we first formulate the stiffness matrix of the given shape, because the stiffness matrix basically depends on the shape of the material, and then we mesh it, and then we solve the system of the equation, and then we find out the displacement. So stiffness matrix are formulated for a given shape of the element. So stiffness matrix depend upon the shape of the element. We will see how in the future. and then it is meshed as we and then the equation is solved, and then we find the displacement. Next one is stiffness formulation methods. So what is common in this elasticity, rigidity, and stiffness? So basically we get elasticity from stress and strain curve. It is basically a material property which doesn't depend upon the force applied. While the rigidity is E times A, which depends upon the area of the material, and stiffness is EA by L. So this is the relation between them, and as you can see, these are different kind of materials and the same kind of force is applied, but the stiffness of cast is more than mild steel, and mild steel stiffness is more than aluminum. This is a material property and it doesn't depend upon the force applied. Okay, so methods to formulate the stiffness matrix. How do we formulate? How do we create the stiffness matrix? So basically, there are three methods. First one is the direct method. It's quite easy and but it's quite complex to program. There are other two methods which are easy to program, which are variation method and weighted residual method, but it's quite complex to understand. But these are two methods which are basically used in the computer for calculation. So to make it simpler, how do we formulate the stiffness matrix? Let's discuss about the direct method using the 1D element. So let's say this is the bar we have and it is fixed in one part. So force is applied here. So from this equation you can see that stress is equal to F by A and strain is U by L. U is the deformation. So as it is a 1D element, so only the deformation happens in the degree of freedom is 1. That means the stress is along the x-axis. So from this equation we can get that the stress is equal to epsilon times E. So that means force is equal to AE by L. That is AE by L is basically the stiffness times the deformation. So as conservation of law says, the total force is basically 0. That means Fi plus Fj is equal to 0. Therefore, Fi is equal to minus Fj. So in case 1, if the deformation is greater here but 0 here, so we get that Fi is equal to this, but Fj is negative of Fi. So we get this equation. So we have Fi as well as Fj. If in the case Ui deformation here is 0 but here it's non-zero, in that case we have this expression. And if we take both the cases and we find that Fi is equal to this expression adding these two cases and Fj is equal to this expression adding these two expressions. Okay. Now we formulate these two equations in a matrix format like this. Okay, and this part is basically called the stiffness matrix. Let's see about when we use two rods. So there are two rods with different area and different elasticity and different length, and they are basically binded here, and you apply force. As we divide this body in free body diagram, so we see the force is divided equally, but we have four sections of deformations. So F1, F2A, F2B, and F3. So if we create the matrix form of this similar kind of like this, we will get the expression for first bar, and for second bar we get the expression like this. When we add these expressions, we get such a matrix. Okay, and when we combine and add this stiffness matrix, we get such a big global system of equation, which is called matrix system of global body. So let's talk about the process. What kind of process is involved in FEA? So first is the pre-processing thing. So in this case, we simplify or clean the geometry. For example, if a fillet or chamfer is there, and if the whole system is bigger, then we just remove it. And then we apply the material properties, mesh it, and also apply the boundary conditions. Next one is this analysis part, which basically depends upon the type of analysis, type of software you are going to use, solution steps, and settings. Third one is the post-processing, in which we extract the stress and strain results out of the calculation, we plot and graph it, and visualize it. Okay, then the next part is about the analysis types. So how many types of analysis are there? For any given problem, it depends upon the situation, what kind of environment the problem is happening. So for that kind of environment, different types of analysis are there. So first type is static, dynamic, explicit, fatigue or durability, thermal, optimization are there, higher analysis, CFDs. So in each type of analysis, there are subdivisions. In static analysis, where it doesn't depend upon the variation with the time. In that case, we use linear analysis. There are non-linear analysis also, quasi-static analysis, contact bolt joint simulations, leakage interference analysis. In dynamic, we have modal analysis, transient dynamic analysis, frequency response analysis, spectrum analysis, multi-body dynamics. Third one is explicit analysis, impact analysis, drop test, car crash. Okay, it's not CAD crash. Car crash analysis, projectile impact, car crash again analysis. Then fatigue durability analysis was there, in which stress and strain life approaches are analyzed. Then fatigue analysis for ASME and DNV standards. Then thermal analysis of the steady state thermal analysis, transient thermal analysis, coupled thermal analysis, transient weld analysis. Then different kind of optimization there to better the given model. So basically size, shape optimization, topology optimization, topography optimization. Then the high-end analysis are mold flow analysis, multi-physics analysis, manufacturing simulation, noise vibration harness. Then fluid dynamic analysis, basically pressure to operation and the flow characteristics there. Cavitation study, thermal transient flow analysis, laminar turbulent flow, and flow coefficient and pressure recovery. So there are many kind of analysis there. Each one has to be studied in detail. You will see in this future. And what kind of softwares are basically used. So there are to design the model of the problems we use CAD softwares, which are there are many commercial as well as freewares. So in Autodesk software basically gives AutoCAD and Inventor. Siemens has their own Creo, Pro Engineer, Unigraphics, Solid Edges, and Dassault Aviation has CATIA, most powerful, and SolidWorks Draft Side. ANSYS has their Space Claim Design Modular, then MicroStation, TurboCAD, and others. And freeware there are Open SCAD, FreeCAD there. And for CAE to analyze the given problem, so mostly the famous commercial softwares are ANSYS, which is Fluent and CFX, Abacus, Nastran, Hypermesh, LS-DYNA, Autodesk CFD, ANSA console are used. There are freewares, which are some of this is ANSYS with storage version, and SimScale is also giving a good thing. Visual FEA, so these are few.